Damped harmonic oscillations. The physical situation. A guitar string stops oscillating a few seconds after being plucked. To keep a child happy on a swing, you must keep pushing. Although we can often make friction and other non-conservative forces negligibly small, completely undamped motion is rare. In fact, we may even want to damp oscillations, such as with car shock absorbers. The simple harmonic oscillators describes many physical systems throughout the world. But early studies of physics usually only consider ideal situations that do not involve friction. In the real world, however, frictional forces such as air resistance will slow or dampen the motion of an object. Sometimes these damping forces are strong enough to return an object to equilibrium over time. The simplest and most commonly observed case occurs when the frictional force is proportional to an object's velocity. Note that other cases exist which may lead to nonlinear equations which go beyond our scope. In engineering practice, we are almost invariably interested in predicting the response of a structure or mechanical system to external forcing. For example, we may need to predict the response of a bridge or tall building to wind loading, earthquakes, or ground vibrations due to traffic. Another typical problem you are likely to encounter is to isolate a sensitive system from vibrations. For example, the suspension of your car is designed to isolate a sensitive system, that is you, from bumps in the road. Electron microscopes are another example of sensitive instruments that must be isolated from vibrations. Electron microscopes are designed to resolve features a few nanometers in size. If the specimen vibrates with amplitudes of only a few nanometers, it will be impossible to see. Great care is taken to isolate this kind of instrument from vibration. That is one reason they are almost always in the basement of a building. The basement vibrates much less than the floors above. We will use a spring mass system as a model of a real engineering system. Consider an object of mass m attached to a spring of constant k. Let the damping force be proportional to the mass's velocity by a proportionality constant b called the damping constant. We can describe this situation using Newton's second law, which leads to a second order, linear, homogeneous ordinary differential equation. We simply add a term describing the damping force to our already familiar equation describing a simple harmonic oscillator to describe the general case of damped harmonic. Damped harmonic oscillator. Let us consider a spring of force constant K suspended from a rigid support. The free end of the spring is attached with a block of mass m, which makes the string extend by a small amount, say x, which attains an equilibrium position when the weight of the block balances the elastic restoring force of the spring. That is, mg is balanced with kx. Now from this equilibrium position, if the spring is extended or compressed by moving the block, again the elastic restoring force acts so as to attain the new equilibrium and the spring is set into oscillation. Let us consider the damping force Fd, which is proportional to the velocity, and the restoring force, which is proportional to the displacement. The restoring force is directed towards the mean position, that is always opposite to the displacement, hence the negative sign. The damping force is opposing the motion, that is opposite to velocity, hence the negative sign. So the damping force is negative Bv, where B is the damping constant of the medium, and the restoring force is negative Kx. The net force on the system is sum of the damping and the restoring forces. So the net force, which can be represented as mass times the instantaneous acceleration of the system, is equal to negative bv plus negative kx. Acceleration is the time rate of change of velocity, and velocity is the time rate of change of position. So ma is written as md square x by dt square plus b dx by dt plus kx is equal to 0. That is by taking the terms from the RHS to the LHS. Dividing throughout by m, we have d square x by dt square plus b by m dx by dt plus k by m x is equal to 0. B by m is written as 2 beta, where beta is the damping coefficient of the medium, and k by m is omega naught square, where omega naught is the natural angular frequency of the system. So replacing, we have d square x by dt square plus 2 beta dx by dt plus omega naught square x is equal to 0. This is the differential equation of a damped harmonic oscillator. Now rewriting it again, we have d square x by dt square plus 2 beta dx by dt plus omega naught square x is equal to 0. To obtain the general solution of the differential equation of the damped harmonic oscillator, this equation being a homogeneous second order differential equation, we can use one of the mathematical methods. The solution should be either containing a sine and cosine term or an exponential term. We follow the latter. So let us assume that x is equal to a e raised to alpha t be the solution. This is an assumption, we will be checking on that, where a is a constant and alpha is a variable. Since the equation has the first and second derivatives of x, we will find dx by dt as well as d square x by dt square. So on obtaining the first and the second derivatives of x, we will substitute this in equation 1, which is the differential equation of the damped harmonic oscillator. So substituting, we have a alpha square e raised to alpha t plus 2 beta a alpha e raised to alpha t plus omega naught square a e raised to alpha t is equal to 0. Now we can take the common terms a e raised to alpha t multiplied by alpha square plus 2 beta alpha t, 2 beta alpha plus omega naught square is equal to 0. Now the product should be equal to 0 means one of the terms should be equal to 0. A e raised to alpha t, the assumed solution cannot be 0. So we take the second term alpha square plus 2 beta alpha plus omega naught square is equal to 0. This is a quadratic equation whose solution can be written in the form minus b plus or minus root of b square minus 4ac by 2a if the quadratic equation is the general form ax square plus bx plus c. So considering alpha square plus 2 beta alpha plus omega naught square equal to 0 as the second equation, we can write the root as minus 2 beta plus or minus root of 4 beta square, as 2 beta is a b term, minus 4 omega naught square divided by 2, the A equivalent term is 1, comparing with ax square plus bx plus c is equal to 0. So alpha is minus beta plus or minus root of beta square minus omega naught square is the value. Since alpha is having two values, as there are plus or minus term in the solution, the assumed solution x is equal to a e raised to alpha t is modified as x is equal to a1 e raised to alpha 1t plus a2 e raised to alpha 2t. Now this becomes our assumed solution. Since we are doing the trial and error method, we found that alpha has two values, so we modified the assumed solution. Now, substituting the value of the two alphas, alpha 1 and alpha 2, from the obtained relation, we can modify the assumed solution as a1 e raised to minus beta plus root of beta square minus omega naught square into t plus a2 e raised to negative beta minus root of beta square minus omega naught square times t. This can be rearranged by taking the e raised to negative beta t term common, and this is the general solution of the differential equation of a damped harmonic oscillator. So x is equal to e raised to negative beta t, a1 e raised to root of beta square minus omega naught square into t plus a2 e raised to negative root of beta square minus omega naught square into t. Since the general solution contains beta and omega naught, beta being the damping coefficient of the medium, which is b by 2m, so depends upon the oscillator as well as the medium. Omega naught is the natural angular frequency that corresponds to 2 pi times the natural frequency, and natural frequency is the frequency with which an oscillator oscillates in undamped conditions. Now, since the general solution contain beta and omega naught, and they can have different values, so depending upon the relative values of beta and omega naught, we will have three different cases for the general solution. Now let us move forward for the case 1, where we can consider beta less than omega naught. So using beta less than omega naught, we can see that root of beta square minus omega naught square will be imaginary. So let us write root of beta square minus omega naught square equal to square root of negative 1 into omega naught square minus beta square. So we have modified this equation, the term. So root of negative 1 is I, the imaginary term. So we can write as I root of omega naught square minus beta square, which is equal to I omega, where omega is root of omega naught square minus beta square. Now let us use this term in our general solution. So x is equal to e raised to negative beta t, a1 e raised to omega t plus of course I omega t plus a2 e raised to negative I omega t. Now we can expand e raised to I omega t using e raised to I theta is equal to cos theta plus I sin theta, and e raised to negative I theta is cos theta minus I sin theta. So using that, e raised to negative beta t is a1 e raised to I omega t is replaced with cos omega t plus I sin omega t. Similarly, in the next term, a2 e raised to I negative omega t is replaced with cos omega t minus I sin omega t. Now you can see that there are terms containing cos omega t and I sin omega t common. So expanding and taking common, we have a1 plus a2 cos omega t plus I a1 minus a2 sin omega t multiplied by e raised to negative beta t as x. Now this seems to be somewhat stretched a bit from the general equation. So to simplify, let us take the constant term a1 plus a2 equal to a0 sine phi. We will find the value of A naught and phi shortly. And A1 minus A2 multiplied by I equal to A naught cos phi. So using that in the previous equation, we have x is equal to e raised to negative beta t, A naught sine phi cos omega t plus A naught cos phi sine omega t. Now you can take A naught common and find that a term like sine A cos B plus cos A sine B formed here, which will be sine of A plus B. So A naught e raised to negative beta t multiplied by sine A cos B plus cos A sine B form. So we will be writing it as sine of A plus B. That is, here it will be sine of omega t plus phi. This is the solution for case 1, which is known as the underdamped condition. Examining this term, we can see that we have sine of omega t plus phi, which is a periodic function. So definitely the motion will be oscillatory. And with the term, the exponential term e raised to negative beta t, we can say that the initial amplitude A naught will be decreasing with time. So we have a periodic motion with exponentially decreasing amplitude over time. This is the underdamped case, case 1, where beta is less than omega naught. That means the damping coefficient is less than the natural angular frequency. The time period of oscillation is 2 pi by omega. Remember, omega is the root of omega naught square minus beta square. So the time period for undamped oscillation means the ideal condition will be 2 pi by omega naught. And for the underdamped case, that is the case 1 here, the time period will be 2 pi by omega. So we can say that the time period for underdamped case will be greater than that of the undamped case. T will be greater than T naught. So due to underdamping, we have a case in which the time period increases and amplitude decreases exponentially with time, so a periodic motion. Now let us examine case 2, in which beta is greater than omega naught. So we can see that the root of beta square minus omega naught square will be a real quantity, and let us write that. Case 2 is known as the overdamped condition. Remember, case 1 beta less than omega naught is underdamped, and case 2 beta greater than omega naught is overdamped. Now using a beta dash is equal to root of beta square minus omega naught square, the general solution can be modified as a1 e raised to negative beta plus beta dash t plus a2 e raised to negative beta minus beta dash into t. The term will represent an aperiodic motion with exponentially decreasing initial displacement. So the graph will be representing a non-oscillatory motion. The particle or the body attains rest without crossing the mean position. Now let us move on to case 3, in which beta equal to omega naught, which is the only case left. This is known as a critically damped case. If beta is equal to omega naught, of course the root of beta square minus omega naught square term will be equal to 0, which implies that x is equal to e raised to negative beta t a1 plus a2, as e raised to 0 will be equal to 1. a1 and a2 are constants, and the sum of two constants will give you another constant. So x is equal to a constant multiplied by e raised to negative beta t. This is the solution, but for a more perfect mathematical solution, because we want the two constant terms, let us assume that a root of beta square minus omega naught square is equal to h, which is a very small quantity tending to be 0. So that we can modify the general solution as e raised to negative beta t, a1 e raised to ht plus a2 e raised to negative ht. Since it's a term containing e raised to ht, we can expand it with the general form as 1 plus x by 1 factorial plus x square by 2 factorial plus etc., and we can neglect the higher powers as h is very small, so the higher powers will be negligibly small. So the equation is modified as e raised to negative beta t a1 plus a2 multiplied by 1 plus a1 minus a2 multiplied by ht. So a1 plus a2 is another constant, the sum of two constants, and a1 minus a2 is another constant, which is the difference of the two constants. So we have e raised to negative beta t d plus et, which is also a non-periodic motion. The system attains rest at a much faster rate without crossing the mean position. The key terms we have discussed in this section: underdamped, the condition in which damping of an oscillator causes it to return to equilibrium with the amplitude gradually decreasing to zero. System returns to equilibrium faster but overshoots and crosses the equilibrium position one or more times. Critically damped, the condition in which the damping of an oscillator causes it to return as quickly as possible to its equilibrium position without oscillating back and forth about this position. Overdamped, the condition in which damping of an oscillator causes it to return to equilibrium without oscillating. Oscillator moves more slowly toward equilibrium than in critically damped systems.